All right, couple of reviews, because these are the things that are in that very long final exam project. Kind of go through some things. So not doing all of them, but we haven't done triangles in a while. Triangle LMN, given the following information. So, well, hold on a minute. Pen's dead. So LMN, you go ahead and draw your triangle. Put the letters LMN somewhere. Doesn't matter. LMN. Lowercase letters are side. So I got 810, 620, and then N is 166 degrees. Find the length of side N. How do I find side N? This kind of problem. Bum, bum, bum.
It's been a while.
Law of cosines. Anytime you have side angle side, law of cosines will help you find what you're looking for. So we have the angle. We don't know the measure of the opposite sides. The way the law of cosines works is the side opposite of your known angle, in this case N, be squared, is equal to the sum of the squares of the adjacent sides minus double their product times cosine of the angle in between them. And then I go solve for that. So somebody type that in, tell me what we get for N. Make sure your calculator's in degree mode. It does matter here because you're putting a number inside of a trig function. Thousand hundred and 11.71. Ivan, what you got? A lot of people forget to take the square root of their answer. I get it. Do what? Huh? Liam, did you get that?
I got 14,019.
Oh my goodness.
See the square root? Yeah. I like do it.
You're in radiant, man. All right.
Yeah, I got 14,000.
Well, all right. It's who up? 14,000 what?
No, it's just 1,919.
1,419.
0.5. You want how many decimal places you want to do?
Give me one.
0.5.
0.5. All right. Let's see. Let's try it again. Let's do this one. Triangle STU. Find the length of length. How about measure? Measure of angle U. So draw my triangle. STU. S is 360. T is 110. U is 450. We want to find the measure of angle U. Right here. Three sides and no angles. This law of cosines also. So side opposite the angle reference squared is equal to the sum of the squares of the adjacent sides minus double their product times cosine of the angle. This one's different. A few more button presses. Gonna have to, a most common mistake is typing this whole thing in and then pressing enter before you get the cosine. It don't fly that way. You gotta subtract the 360 and the 110 squared over. And then you divide by these three numbers. And that'll give you a decimal that you do inverse cosine of.
Right to the number.
I would do, well, I guess technically you could do solver cube, couldn't you? I would do 450 squared minus 360 squared minus 110 squared. And press enter on my calculator.
450 squared minus.
Minus the 360 squared minus 110 squared. That's going to give you,
6.
yeah, is equal to, and I'm going to go ahead and multiply those other three numbers together. So 2 times 360 times 110, remember it's negative 79,200 cosine of u. Then divide. And you got this decimal here. And then to get u, you'd have to do inverse cosine. So inverse cosine of that, I got 140 change, 146. What I got there. Do this one while we're in Triangleville. Triangle KLM's got the bit of information. Find the length of side L. 140.146 degrees. All right, KLM. KLM. M's 160. Ooh, not drawn the scale. 145 degrees there. 28 degrees here. Find the length of side L. Well, we do have the measure of an angle and the length of its opposite side. So this is a candidate for law of sines. Because law of sine says that inside of a triangle, sine of an angle divided by the measure of its opposite side will produce a ratio that is consistent amongst all sides and angles within a triangle. So if I could get side or angle L, I could do the same thing with side L to help me solve. What's the measure of angle L? Add up the two angles, take them away from 180. 7. Now I just solve for L. Cross multiply. And then divide by whatever sine of 145 is. That give you L. So 160 sine of 7. So you close your parentheses, divided by sine of 145. Yep. 996, whatever. It'll tell you how to round. It's in here. All right, let's see what we got. Let's go back to limits now. All right. Find the values of A where the limit as x approaches A is equal to -3. Yeah. Where does that happen at? Not -5. If you're reading this limit, what kind of limit is that there? If there's no directional indicator behind it. Both ways. So basically you're asking yourself, what x value goes to y is equal to -3 from both sides?
Oh.
That's what you're looking at. Well, -3 for y, get off my screen, is right there. Is there any part of the graph that goes to that highlighted area from both sides without breaking? Like this one goes to -3 from the left, but it doesn't from the right. It goes down here. So that one doesn't do it. This one goes to -3 from the right, but the left side goes somewhere else. Nowhere. Answer's nowhere here. D and E, no solution. No x values. Left and right sides would have to come in and converge on a point. Like if you're tracing with your fingers would have to touch at a place, and it'd be at y is equal to -3. Let's see this one. What's the first step in evaluation of limits?
Plug in 6 for x.
Yeah, plug in 6 for x. Ivan said go to Mathway. Put put 6 for x. It makes the bottom 0. What does it do on the top? 36 minus 24 minus 12, 0 on the top. 0 over 0. What does that mean? Something. Indeterminate form.
Yeah.
What that means is we don't know what the answer is. You got to do work. So what is our method in this kind of problem? Factor. You can factor and cancel. All right, so becomes the limit as x approaches 6. The bottom's x minus 6 times x plus 6. 6 and 2 in the top, minus 6 plus 2. X plus minus 6 is a cancel. Write your simplified form. And now plug in again. So now we plug in 6, and we get 8 over 12.
4 2/3.
My brain locked up there.
Photo math works. Miss. Photo math works, boys. Let's go. You got it. I was waiting to see what the answer was before.
No. This one here. Limit as x approaches 4.
1/4 final answer. Find out.
Put 4 in, you get 0 over 0, indeterminate form. What did we do on Monday with this?
Factor.
Nope. You didn't factor this.
Oh, you multiply.
I multiplied by what?
The X minus two, the X plus one.
Not that part. It's the,
Oh,
it's the part that's got the square root in it. Square root of x plus 2. Multiplied by the conjugate. All right, pen died. Give me about 15 seconds. I get enough to finish this.
We haven't got the new review yet.
New review?
The new stuff.
Yeah, but that stuff goes quick.
New review. I have the best logic in the school. It don't even come.
All right, so multiply it out. Strategically though, I'm not gonna FOIL out the bottom because we're hoping that we can get the x minus 4 to cancel. Because it made the denominator 0. The top, when you multiply it out, you got a difference of squares. So I'm just gonna end up with, that's gonna make x minus 4. Square root of x times itself makes x. Negative 2 and positive 2 make minus 4 is no middle term. X minus 4 is cancel. It makes an equivalent form as the limit as x approaches 4 of 1 over the square root of x plus 2. Now you put in 4. 1 over the square root of 4 plus 2 is 1/4.
And I would like. What would we do without that?
Have to learn something.
I was gonna say actually learn it with my hand. Do it with my hand.
All right.
Doesn't change things.
No, you have to pay money for that.
Uh-huh. For what? Oh, Mathway makes you pay for this. Mathway makes you pay for this.
So we all use the little cheater apps now? Everybody in the school uses cheater apps. No wonder why nobody does the Desmos assignments, because the photo map doesn't help with that.
No. How do you think I was able to do so many kids' schoolwork last year in such a short amount of time? We just weren't smart enough to use those.
I don't want to know that.
And they are like, click.
All right, so today and tomorrow are the last two days of new stuff per se. We're going to evaluate limits that deal with infinity, but this time we don't have the graph to look at. And let's start here with this, and then I'll go back to the top. Evaluate the limit as x approaches infinity, and we look at what we're given. Now, you can't necessarily just put infinity in because I can't treat it like a number. Infinity is a behavior. And if I'm looking at the equation or the expression inside of the limit, you got to think about what some characteristics are here of this kind of function. It's a polynomial. Polynomials don't have horizontal asymptotes. One side's going up, one side's going down, or both sides go up, both sides go down. So what I can do is I need to look at the leading term, which it's called a leading term, but it could be written out of order. It's a term with the highest degree. In this case, it's negative x to the 4th power. Leading term test for polynomials, chapter 2. If I have an even degree, that means both sides point the same direction. The number in front's negative, both sides point down. Now you can do whatever the heck it wants to in the middle, but left side's going down, right side's going down. And so this limit, x approaches infinity, is asking what's the right side doing. Now, technically, since it's not approaching a defined or a finite value, you could say the limit doesn't exist. I think in delta math, and actually the way that I want it would be to describe the behavior, we'd say negative infinity. Now, graphically, you can technically just type it in Desmos and look at it. I can also always use tables. Tables never fail, really, when evaluating limits either. And we got this one. Similar but different. Limit, x is heading towards negative infinity, so basically left in behavior. I have a polynomial. Biggest degree term is not in front this time, it's in the back. Odd degree negative coefficient. Odd degree means left and right sides go opposite ways. Negative number out front. Think about your x cubed graph but flip. So that means left up, right down. It could do whatever in the middle. It could do like this, whatever. But I'm only looking at the ends. So we're looking at left end. Left end goes up for odd degrees with negative coefficients. So we'd say positive infinity. So what? For those two, they are. Now let's look at a rational function. And we have the same kind of limit. The limit is x approaches infinity. When x is approaching infinity, you need to think in behavior. And technically, if it's x is increased when outbound, you're more specifically the right end. When we were in the rational functions unit, there was a way for us to look at a rational function and determine whether or not it had a horizontal asymptote or not. Well, Desmos is one, but there's something that I refer to as the end behavior model for rational functions, which basically you have three scenarios. So you got a bottom heavy function, which means the biggest exponent's on the bottom. That means you have a horizontal asymptote of the x-axis. You have same degrees. Top and bottom. You have a horizontal asymptote. That is, y is equal to the ratio of the coefficients between, if I had x to the fourth on top and the bottom, it'd be the ratio of the numbers out front. If it was top heavy, biggest exponent in the numerator, there is no horizontal asymptote, which means in terms of our limit, the answer would be either positive or negative infinity. Well, looking at our problem, biggest exponent is x to the fourth. It's bottom heavy here, which means I have a horizontal asymptote of y is equal to 0. That's what this limit equals. So no matter how far to the right you go, the graph's going towards y is equal to 0. So look at this one. Limit as x is approaching infinity. Well, right in behavior. We look here, what's the degree of the bottom? No. This isn't multiplied all the way out. It's technically degree 4 on the bottom, degree 4 on the top. Now, yes, it's going to wind up being ratio coefficients, but the most commonly missed thing is somebody looks here and goes, hey, -2 over -4, 1/2, done. I feel warm and fuzzy about it. The problem is you would have to multiply this thing all the way out to see what that term is. Now, I don't have to multiply it all the way out. I just need to know what is the coefficient of the degree 4 term in the top if you were to multiply it all the way out. The degree 4 term in the top would be if when I took 8x and multiplied it to the -2x to the third. Yeah. And the bottom here would be when I have the 7x multiplied to the -4x to the third, the -28x to the fourth. So that function that we have in here, it's not my increase the size of x without bound. It's going to behave a lot like this one. Well, ratio of the terms, coefficients, -16 over 28. Simplify that, 4 over 7. Two negatives make a positive, yeah. So basically, whatever that function was has a horizontal asymptote, 4/7. Check this one. Dude, I'm gonna be done in just a minute. You about to spring a leak?
Mike, if I give up, that's not good.
What about this one?
That one's top heavy.
Top heavy. Now I only look at that scenario when X is going to positive, negative, infinity. So top heavy, great. No horizontal asymptote. What's the highest degree term in the numerator? Yeah, but it would be negative 3x to the fourth. All right, and the denominator would be what? Negative 25x to the third. So it's top heavy, but I can still identify when we're going to the right, I can still identify the end behavior. Here's what you do. Reduce the problem. Simplify what you're looking at. So basically, this is going to behave the same way that the limit as x approaches infinity. What is that? 3 over 25x does. Well, 3/25 times x. If you go to the right, which way is that graph going? Up, down, or flat?
It's going up.
It's going up because it's got positive slope being done. Infinity. I can reduce it down like this. This is using an end behavior model approach. Reduce it down, see what you're left with, and say if it's a line, figure out positive, negative slope, tells you which way it's going, without having to look at Desmos or a graph to confirm this. Now we get this a funky one. Check this mug out here.
Oh, no bueno. I'm gonna shake this top heavy. Well, this will be to 1/3.
Yeah. What's the
Degree.
Yeah, it is same degree. So check this. You got the cube.
Oh,
You got the cubed root, and then I got that 8x to the 6th there.
which makes it 8x to the second.
Almost. That make it. You got to take the cubed root of 8.
Oh, I don't know that, but
X to the 6th.
to the second. Oh, then. Oh, I mean, I guess you are.
Yeah. So it's that is if I'm only and I only do this for when these x approaches infinity problems. We're looking for biggest degree terms, and because as x gets farther and farther away from 0, the largest growth rate terms are going to dictate the value the most. So I'm looking at the ones I highlighted: 5x squared, and the cubed root of 8x to the 6th is 2x squared. Same degree.
Same thickness.
So what that means is, as x squareds would cancel, I'm going to get 2/5. That graph, I typed it in Desmos, would, as you went off to the right, it'd have a horizontal asymptote of 2/5. Two more. Check this one.
That does not go to infinity.
Bingo. Because Spanky almost said that's same degree. X goes to 2, so we abandon the end behavior model and we go, all right, put a number in, put the 2 in.
Top heavy means there's no.
Top heavy means the biggest exponent's in the top.
Yeah,
But I only do that if x approaches infinity.
I know, but like, what does it mean when it's top heavy? Not.
The answer is going to be either positive or negative infinity.
Well, it's -1/4.
0 on the bottom because you got 4 times 0. And then you got,
Oh, I know. Okay.
and you put 2 in, you get 1 times -1. I get -1 of 0.
Yeah.
What does that mean?
It's 0.
What?
No,
No, that's undefined.
yeah. The end.
Okay, well,
But we gotta define it.
This is different. This is different than having 0 over 0. What do I have at x is equal to 2?
Undefined. I have a hole.
0 over 0 is a whole. You got a vertical asymptote there. Now, the big question that we have is, if I have a vertical asymptote at x is equal to 2, with limits, we want to describe what the behavior is around 2. So we kind of did this when we were trying to graph these things way back in chapter 3. So what you do, if I want to know what the behavior is, well, riddle me this. As I come to 2, as the graph goes to its vertical asymptote, what are its options?
It's going up.
It's going to positive infinity or negative infinity. So what we're going to do is we'll make a sign chart here. Like rational inequalities. What you do is you put every number that makes the top and the bottom 0 on this, and you got to put them in order. So what have we got? -2. 1, 2, 3. Now, I don't have to test around all the numbers because I only care about this one. What is happening as I come at 2? Because technically it's undefined.
Where did you get the 1, 2, 3 from?
1 makes the top 0, 3 makes the top 0, -2 makes the bottom 0, 2 makes the bottom 0.
Oh.
You put all of them on the number line because what they do is they make sure that you don't go too far away from the number you want to test around.
Oh.
So what I'm going to do is I'm going to pick a number inside of this interval like 1.5. Put it in for x. Tell me if it's positive or negative. 1.5 minus 1, positive. 1.5 minus 3, negative. So I already forgot. I got positive times negative over 1.5 plus 2 is positive. 1.5 minus 2 is negative. That is going to be a positive. Guess what you just figured out? You just figured out that the limit as x approaches 2 from the left, I'm going to be lazy. I'm going to call this f of x. It's going to positive infinity. What you just figured out. Now let's do the same thing between 2 and 3. So like 2.5. Play the sign game. 2.5 minus 1, positive. 2.5 minus 3, negative. Over 2.5 plus 2, positive. 2.5 minus 2 is negative. Positive. Positive. I fixed myself. So that means negative here.
So it's going up and down.
This side, as we come at 2 from values bigger than 2, it's going down. So the left side of 2, vertical asymptote goes up. Right side of 2, the vertical asymptote goes down, which means that this two-sided limit, we actually have no option other than to say that this does not exist. If they both went the same direction, I could say infinity or negative infinity, but they don't. So I got to say D and E. Nothing I can do. Handcuff. All right. Next one. Last one, I think, right?
Yes, sir.
Last one. All right. How do I start?
Plug in 4.
Plug in 4. What happens when I put in 4?
16 plus 8
Is 24 minus 15 is 9.
All right. Fingers crossed. Give me a number down here, then 0. Dang. 9 over 0. What does that mean we got?
All signs. Or no, sign chart, I mean.
Yeah, but number over 0 means you have a what at x is equal to 4.
Oh, vertical asymptote.
That's right. You got to make that connection. So I'm going to do the sign chart thing again, but to do that, your life's going to be so much easier if you factor your problem.
We didn't do this last time.
The other one's already factored, wasn't it?
Shoot.
Yeah. So we factor, what's that? X plus 5, x minus 3, and then the bottom minus 4 plus 2. All right. So we're going to make a sign chart. A straight line there. all the numbers that make the zero on the top and the bottom. So -5, -2, 3, and 4. All right, and we are only concerned with how is it behaving around 4? Oh, this, I'm only gonna test it around that number.
3.5,
Sure. Put 3.5 in,
so you got positive, positive,
Negative, positive.
which
It
makes
it negative.
makes a negative, right?
And then we'll say 5.
All right, then we say 5.
positive, 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 let's make it positive.
That's right. So what we've determined is the behavior around there. So the limit as x approaches 4 from the left, because we ended up with a negative sign, I'm going to be lazy to write f of x, it's going to negative infinity, because it's always producing a negative sign in between 3 and 4. The limit as x is approaching 4 from the right, this function of x, because it's always producing a positive sign, it's got to go to positive infinity. Since these two are different, we can't write an answer as positive or negative infinity. We have to say does not exist.
All right.
All right, that's all I got because we have more than a lot of work to do. Work on things.